what I'll be talking about is how we can use different frameworks from quantum contextuality to describe natural language data. So first of all, I'll briefly explain which frameworks of contextuality we have been using and which features of natural language we've been looking at as well. In the second part of this talk, I'll explain how we found some instances of models arising from natural language that were found to be contextual. And finally, in the last, so in this framework, contextuality can be seen as the impossibility to find a global section of this pre-sheaf, which is compatible with the observation. So that is the observed probability distributions or just distributions overall. And in particular, what has been shown is that in some cases, you don't actually need the whole probability distribution, and you can decide from the support of the distributions only whether a system is contextual or not. However, the main drawback of this framework is that technically speaking, we can only deal with no signaling systems. And that will be a problem in the data that we have obtained, as we'll see in the next sections. So the other thing that is quite convenient that we're taking from the shift theoretic contextuality is that we can use bundle diagrams in order to represent, in particular, possibilistic models. So once again, I'm going to go briefly over this. So we start at the base of the diagram, and we represent all the local measurements by vertices or zero simplices. And then we add the compatibility structure. So that is whenever a joint measurement is possible, we can add an edge. And we do that for all the possible measurements. And then once we have this measurement structure, we define fibers on top of it. And this will be used in order to store the possible outcomes that we observe. So for example, if we consider the first context, measurement context AB, you can see that the joint outcome 0, 0 comes with a non-zero probability, therefore we can add an edge. And in fact, in this context, all the outcomes are possible, so we do add all of the possible edges. However, in the next context, we can see that the joint outcome 0, 0 is not possible, therefore we don't add anything. And for the other one, we add the corresponding edges, and we can continue and fill in the whole bundle diagram. So from these bundle diagrams, we can already see that this model is contextual, and we claim in particular that this local section here cannot be part of a global section given the observations that we have. And this can be seen by consistently trying to extend this local section, and what we obtain is that at the local measurement B, we have an inconsistency, and therefore this model is in fact logically contextual. So the second framework that we have used is the contextuality by default framework. So there has been very many talks before me in the previous sessions that have been talking about this framework in a lot more details than what I'm going to do now. So I'm just going to introduce what we have actually been using for our work. So in CBD, the measurement between contexts are fundamentally unrelated. So for example, if we go back to this example, then local measurement B in the measurement context AB and in the measurement context AB prime are considered as being completely unrelated. And therefore, instead of identifying these local measurements or contents, we want to maximize the probability that they agree. And in particular, this allows us to analyze signaling systems. And another motivation for us to use CBD is that we can have a very general definition of context. So that can mean that, for example, we can add orders in which contents are measured, or things like how the probability distributions are collected, or other kind of extra information. So in this talk, I'll mainly focus on cyclic systems. So just to remind ourselves, a cyclic systems is a system in which all the content variables are binary, and each context has two contents, and each content is contained in two contexts. So in particular, we'll focus mainly on rank 2 and rank 4 examples. And if we take a notation that is similar to the bundle diagrams, we can see that this corresponds to systems where the base is a connected loop. And the main advantage to use this type of systems is that we can check the contextuality or the non-contextuality of the system by just checking whether this inequality holds. And in particular, the quantity delta that is presented here can be seen as the degree of signaling at the system, and we'll use that a lot more in the last part of this talk. So in order to introduce more about what I'll be saying in the last part of this talk, we have to take a small detour via M-contextuality that has been developed by Matt Jones, and that has been introduced as well before. So once again, not going to go into too much details. So the idea is that we want to model observations using a canonical model. And in particular, what we're going to use a lot from this framework is that we can quantify the degree of direct influence given a canonical model from the context into the content variables. And in particular, a system is said to be M-contextual if you can find a canonical if you cannot find a canonical model which minimizes all these direct influences. That's what's been said here. So as Matt Jones has actually said before as well in his talk, is that M-contextuality is equivalent to CBD contextuality. And something else that we'll use in the last part of this talk is that there is a relation between the degree of signaling of the system delta that is coming from CBD. There is also a relation with the minimal possible degree of direct influence that is allowed by the observations that we have. So now we move on to the features of natural language that we've been looking at. So in particular, we focused on ambiguity. And that is a major topic of both psycholinguistics and computational linguistics. So there are different types of ambiguity that arises in natural language. The first one is lexical ambiguity. So that is whenever a word has multiple possible interpretations. So for example, in the sentence, the beach was mine. Was there some mines, so some bombs on the beach, or was there some miners looking for minerals? Similarly, in the sentence, I saw a log, was I seeing with my eyes or sawing with saw? And finally, in the sentence, they can fish. Here we have the whole phrase can fish is ambiguous because either they know how to fish and they know how to catch fishes, or they put fishes in cans. A second type of ambiguity that we have is called syntactic ambiguity. So that is when all the words in the sentence are unambiguous, but the sentence itself can have different interpretations. So for example, if we consider the example, I shot an elephant in my pajamas, was it me or was it the elephant that was in my pajamas? So that is called attachment ambiguity. And another example is in the sentence, he bought blue socks and hats. So in this case, were the hats blue as well as the socks? That's unclear, and that's sometimes referred to as scope ambiguity. One last type of ambiguity is called coreference ambiguity. So that can be seen in the sentence, John put the ball on the plate and it broke. So here it is ambiguous whether it refers to the ball or the plate. And this type of ambiguity gave rise to the vinaigrette challenge, which is very similar to the Turing test. So the last sentence is an example taken from the dataset. So the man couldn't lift his son because he was so weak. For humans, it is fairly obvious that he refers to the man and not the son. However, it is a lot more complicated to do this type of inferences using computers. So in this talk, I'll mainly focus on lexical ambiguity, and I'll go into more details of what features of lexical ambiguity we can have as well. So a word can be either homonymous or polysemous. So if it is homonymous, it means that it has several unrelated, completely unrelated interpretations. So for example, if we consider the noun pitcher, that can either refer to a type of drug or a baseball player, so clearly unrelated interpretations. On the other hand, a polysemous words will have several related or similar interpretations. So for example, if you consider the noun paper, that can either refer to the paper that you're writing on, or a newspapers or a journal article. So what has been shown in the past in either psycholinguistics or experimental psychology is that humans process different types of ambiguous words differently. In particular, there is a difference in processing between homonymous and polysemous words. So if we focus for now on nouns, because it's easier to see, for homonymous nouns, there is a very marked frequency effect. So that means that whenever somebody encounters an ambiguous noun, a homonymous noun, then straight away you make a first judgment about which is the most common meaning that it should have. So that is depending on your personal experience. And then you will use the context, so the rest of the sentence and the rest of the discourse, in order to change these activation weights when you're trying to select the appropriate meaning of the word. And whereas for polysemous words, we don't have actually any frequency effect, but the context effect are a lot marked. So in particular in this talk, we'll mainly focus on context effect and not very much on frequency effect. Another difference in processing that has been shown is between ambiguous verbs and ambiguous nouns. So as we have shown, when you consider ambiguous nouns, then the first stage of the disambiguation happens exactly when you encounter the noun, and then the context, the disambiguation context that you need in order to fully disambiguate it, can be found pretty much anywhere. So it can be before the noun is encountered, it can be after, it can be in a few sentences after. But that is when the second stage happens. For verbs, on the other hand, we observe some type of delay even before the first stage of the processing is done. So for example, in homonymous verbs, what happens is that people will usually wait to know what the arguments of this verb is. So for example, if you have a transitive verb, what the subject of the verb is, what its object is, etc. And for polysemous verbs, this delay is even longer. So people will tend to wait until the end of the clause or the end of the sentence before making a commitment. So now we move on to contextuality as understood in quantum mechanics in natural language. So we start by studying logical contextuality in this type of ambiguous phrases by presenting an experiment that is fairly similar to bipartite Bell scenarios in quantum mechanics. So as in quantum mechanics, we start with two agents, Alice and Bob, and they're given an initial state. So in our case, the initial state will represent what type of phrase we're looking at. So either it is a subject-verb phrase, or we can switch the order and have a verb-object phrase, or we can have completely different grammatical types. So for example, an adjective-noun phrase, or something even more general. So we just say, for example, that we know that the verb, the word A happens before the word B. And then once we fix this initial state, the agents are given a list of words that they can choose from, and they can make a choice. So for example, in this scenarios presented here, Alice can choose between in a list of subject, and Bob can choose from a list of verbs which phrase they're going to look at. So for example, if Alice chooses the noun boxer and Bob chooses the verb lap, we'll be looking at the phrase the boxer laps in this case. And then once they made the choice, we can collect the different outcomes and compute the probability distributions. And in order to do that, we need to label the different meanings and different senses that we're considering. So for example, for the ambiguous noun boxer, we can label the athlete practicing boxing as 0 and the boxer dog as 1. So first of all, we'll look at possibilistic models. So the main advantage for using possibilistic models is that we don't need to know the whole probability distributions, and all we need to know is whether a meaning combination is possible or not. And therefore, it is fairly easy to compute this type of tables and draw bundle diagrams. So as we can see, the sections highlighted in red cannot be extended to consistent global assignments. However, this is entirely due to the fact that the support of the distribution is actually signaling. And so technically speaking, we cannot use the sheaf-theoretic framework to analyze this scenario. On the other hand, we have found some example of possibilistically no signaling models, which were contextual as well. So that is one example of such models. And therefore, we can say that there are some models that are logically contextual in natural language. So in order to further analysis, we tried to extend this analysis to probabilistic models. So in order to do that, we collected probabilities from corpora. And we've used two main corpora for that. So the first one is the British National Corpus, which has 100 million words and a lot of different types of documents. And the second corpus we used was the UK-wide corpus, which is a little bit bigger and has 2 billion words and has been constructed from web pages that has .uk domains. And what we found is that all the models that did have a probabilistic model were all signaling, in fact. So therefore, we move on to the contextuality by default framework. And we start by noticing that most of the examples that we considered before, so the Bell type scenarios, were actually cyclic systems of rank 4. However, no contextual examples, CBD contextual examples of this type has been found yet. But that has been partly because the data that we obtained from corpus was not ideal in the sense that some meaning combinations that were clearly possible didn't occur, and some very improbable meanings happen in a lot more frequently than very obvious ones as well. So instead, we're going to focus now on cyclic systems of rank 2 because they're a bit easier to deal with. So in our case, that means that we have two words that can be found in two different contexts. And we in particular focused on the situation when you have a verb and a noun that can either combine as a verb object or subject-verb context. So for example, if you consider the verb eat and the noun chicken, then we can easily see that both verb object and subject-verb context are possible. And therefore, it is a valid scenario. So we found two instances of CBD contextual examples arising from this type of models. So the first one was by considering the verb adopt and the noun boxer. So the probability distributions that we obtained from the corpora was as follows, and it can be shown using the inequality that we had before, that this is indeed contextual. And we can also compute the contextuality measure of this model, like it has been described in previous talks as well. So in this case, it is pretty small, actually. And the probability of finding this model to be actually non-contextual, so for example, if we had a larger data set or a more accurate data set, is fairly high as well. So it's about 56%. The second example that we found to be contextual is by considering the verb throw and the noun pitcher. So once again, the probability distribution is depicted here. and we check contextuality using the same inequality. And this time the contextuality measure is a little bit higher, and the probability distribution to find the probability of finding these distribution to be non-contextual was a little bit smaller as well, and therefore this model is a little bit stronger. So now we move on to something a little bit different, which is the analysis of signaling. So we started with the observation that all the models that we considered were signaling, and that in fact, in both CBD and contextuality, we do have a way of quantifying this degree of signaling. So we wondered whether we could use these numbers to detect a context effect and say something about natural language using these two frameworks. So once again, we're going to here focus on cyclic systems of rank 2 because they're easier and there's less factors to take into account. And we compare the data for the models that we have, depending on which category they're in. So that is whether the verb had multiple meanings or multiple senses, or if the noun had multiple meanings or multiple senses. So we start with the analysis of the quantity delta, or the degree of signaling that we call. So what we found is that across all of these different categories, then the average deltas were roughly the same. So nothing very interesting to see here. Although we have seen some small disparities in the standard deviation. So for example, verbs with whenever verb had multiple senses, or whenever a noun had multiple meanings, the standard deviation was slightly higher. But these were not very marked differences, so we're not really sure if we can say something about this. On the other hand, what is actually a bit more interesting is when we look at the proportion of the direct influence that is coming from the verb or from the noun, in fact. And so if you look at whether the noun had multiple meanings or multiple senses, we see that this proportion here is about 50% in either way. So there was not a lot of difference. On the other hand, if you're interested whether the verb had multiple meanings or multiple senses, in this case we see that the contribution from the verb is actually higher whenever you have a verb with multiple meanings than a verb with multiple senses, and that is to some extent analogous to what has been shown in psycholinguistics ages ago. Because if we recall, so here we're looking at context of two words, so the verb with its object or with its subject. And in order to see frequency effect, this has already passed basically. So that first stage is already done. But in order to have other context effects, you will need a bigger context. Whereas for verbs with multiple meanings, the first stage of this disambiguation happens exactly when you consider this very short context, and that's why we do observe some small changes in behavior here. So briefly to conclude, so we have found some instances of models arising from natural language that were found to be contextual in a quantum-like way. And we have also shown that using frameworks of contextuality to study natural language is actually really interesting because, first of all, from the fact that we have found some contextual examples, it means that we have some limit into the resources that you need in order to represent, classically at least, and the context for computational applications. And we can use both CBD and contextuality to quantify this influence from the context onto meaning selection in ambiguous phrases. So in future work, we would like to have better probability distributions, basically. So we are planning on doing this by collecting human judgment instead of looking at corpus data. We also want to add to further the analysis of the signaling by adding some causal structure into our data set. So that will mean what causal structure is actually compatible with our data set and what would that mean for our model. And finally, we want to extend the analogy that we have with the work from psycholinguistics. So, for example, we want to investigate the frequency effect, as we have briefly mentioned before. We also want to see whether adding a priming context makes any difference. We'd like to use contextuality as well in order to model Gaudian past sentences. And finally, if we can see some differences in behavior when sentences are created from rules. So for example, from chicken the animal to chicken the meat. And I think this is the end of my talk. So I have some references about the background from our work. Do you have any questions?
I have one question, if I may.
Yes.
Hi. So hello, my name is Iwa Borsuk. I'm from Krakow in Poland. Nice to meet you. Thank you for your talk. It was very, very inspiring for me. So I wanted to ask you one question because the thing you presented is very interesting, and I was just wondering, when you refer to natural language, do you mean only English, or do you study some other languages as well?
So far we're mainly focusing on English, but basically it will be very interesting to see how this extends to other languages as well. So for example, at first we tried to consider word orders in English, but obviously this doesn't extend to every languages. Basically we started from something a bit different that was looking at compositionality in English as well, that uses something that is inspired by quantum mechanics as well, so quantum processes. And we just basically try to see whether we can add contextuality into this framework as well to some extent. So that is why we started with English, basically. But obviously it will be interesting to see what happens in different languages too.